Now, graph-based parsing, which has a big computational complexity, but it can deal with very large, very big and very long sentences. In contrast to that transition-based model, which was only good for very short sentences, although it was fast. Here, graph-based parsing is not fast. It has bad computational complexity, but it can deal with very long sentences that is very nice. So greedy-based, they call short-term mistakes like the transition-based approaches. Those are greedy. And transition-based methods tend to have high accuracy and short dependency relations. I said that, so this is largely due to the fact that transition-based methods are greedy. They can be fooled by the seemingly optional local solutions. So they can be fooled, so this is not good. That's why we need graph-based parsing. But there is a disadvantage for that. So it have to make local independence assumptions, which is not good. But the advantage is that it can find exact best global solution via dynamic programming algorithm. So what is a graph-based parsing? Unlike transition-based systems, a graph-based systems explicitly parameterizes model over substructures of a dependency tree. Instead of indirect parameterization over transitions used to construct the tree, it's very easy. You just need to create this score, and you learn this score. So this is the graph-based parsing. For example, you have lots of nodes. You see which of these edges, these arcs, increases increases the overall score. And the rule is that you should create a tree. It should not have a loop. And this is the only constraint that you should have. So the score is assumed to factor through the scores of subgraphs. The score of subgraphs. So the graph-based parsing, we can state that any graph-based parsing must define four things. First of all, the definition for a given dependency tree, the definition of lambda, the method of learning lambda, how to learn those parameters. A parsing algorithm, we want to maximize the score of the graph, because the score of a graph is the score of summation of all scores. For example, the score of this, the score of this one, the score of this. If you add them, it should be the maximum score, if in comparison to other trees that you could have created. So our factored models is one of the approaches. So this for every possible edge, you have a score. For example, between Saw and Mary, you have a score. And so you connect all of them together. Don't worry about the loops because it's the initial step. So you have order of n squared edges. And then arc-factorial models, the score of dependency tree is the summation of all of these lambdas. So we want to know which summation is maximized, which configuration makes this summation maximum. And so we can also represent, because the lambda could be probabilities, like those softmax things. And so why not multiplying it? You see, it doesn't make a difference. You just need log. So it doesn't make a big difference. So, for example, this is your problem. And there are lots of, for example, this is one spanning tree, this is another spanning tree, this is another spanning tree, this is another spanning tree. So among these things, for example, this wins because maybe it has the largest scores if you sum all of these, the score of all these edges. So and we use the simplest algorithm, Chi-Liu-Edmonds algorithm, and because the intuition is easy. You just greedily pick just incoming edge. If it forms an arborescence, I mean, it's like a tree doesn't have a loop, it's great. But if it has a cycle, otherwise it contains a cycle. So because arborescences can't have cycles, so we can't keep every edge, just kick it out. So they might get kicked out. So C also needs an incoming edge. Choosing an incoming edge for C determines which edge to kick out. And so we have two stages only: contraction, everything before the recursive call, and expanding, and after the recursive call. So it's very easy. If it is as a loop, just kick it out, and you see it's very easy and a very old algorithm. And finally, you have your dependency tree. This is the overall algorithm of Chi-Liu-Edmonds. So you construct this graph and then return this algorithm. And this needs this contraction in this step. You need to contract it. So it runs this algorithm and then comes back and finally returns your dependency graph. So this is not important. What is important is arc scoring. Because how do you learn? How do you know which score is better for which edge? So that's why we need to create some features and then learn the training data and those things that we do in machine learning. So the features can look at source, head, and the destination, the child, and arc label. For example, you can think about number of words between head and child. For example, you can see number of words between them. For example, between this and this, or anything else. A sequence of part of speech tags between head and child. Is head to the left or to the right of the child? You have a sentence. If, for example, what are the nodes between them? What are the things? So all of these are features. Vector state of recurrent neural net at head and child. Vector embedding of the label, because each label has some embedding. I mean, in the vector space, it has some numbers. So I used the example from Professor Goyal in India, and he's a really nice teacher, and an amazing scholar. So this is his example. So between saw and with, we can think about in between part of the speech. For example, 1, 2, 3. We have 3, for example, or you can think about head left now. And if this is now, you could have binary relation. So this feature could be either 1 or 0, or you could have some numbers, and you can work between combination of all things to create your features, because you need to learn. Another example is, for example, the arc distance is 3, 1, 2, 3. The arc direction is right, from left to right, so it's right. So you can work with these, for example, 3, 1. So this is the feature vector for this. And you learn it, because now you have the features, you have these features. You want to learn this W. So the inner product of them, you get lambda, which is the score, and you can learn that. So you can also have more features, of course. You can have identity of part of speech tag for WI+1. And all of these could help for learning them. So you want to maximize this. So you have already provided this. You just need to learn this. And in this book, he uses the simplest thing that you could imagine. The first simple perceptron. No special nonlinearity. Because we don't want to do maybe overfitting or those things. So the simplest things that comes to head is perceptron. If this gap goes to 0, it means that W is converged. So we have the weights, the proper weights, these weights, in order to calculate lambda. And lambda, if you get lambda, that's enough. Then you know the dependency parsing. When you feel a peaceful joy, that's when you're near the truth. Yesterday I was clever, so I wanted to change the world. Today I'm wise, so I'm changing myself. Somebody should tell this to Putin that is destroying the world, the order of the world.